Good afternoon. This is Professor Arnold, and today we're going to look at hypothesis tests for mean. So we're going to do this by an example. So let's get started. Here is the example. A data set includes data from 400 tornadoes. Use the tornado's length, which is in miles, to test the claim that the mean tornado length is 2.2 miles. Use a 0.01 significance level. The sample mean and standard deviation were 2.31592 and 4.3078 miles, respectively, suggesting a larger mean length. Okay, now you would notice that I have the numbers that are in this problem in red, except for the 400. I just forgot to do that one, but that one is also true. Okay, I mean, it's true that it's a number. So we need to write down things. Let's write down n equals to 400. I will write that down myself. Use the tornado's length to test that mean is that. So here they're saying that the established mean is 2.2 miles. So the established mean is mu 0. So you write mu 0 equals 2.2. Write this down. If you don't write it down, you would not understand the rest of the presentation, because I'm going to refer back to them as we go along, and you would not see the slide anymore. Use a 0.05 significance level. So here you would say alpha is equal to 0.05. Alpha is the level of significance. So I'm not making up anything. I'm just saying, let's write all of these numbers with the associated variable. Then now it says the mean, and they were talking about the mean of a sample. So this would be x bar. So you say x bar is 2.31595, and then the standard deviation, which is Sx or S, is equal to 4.30786. Okay, so we have those. Now let's see, what is the question asking us for? It's asking us to identify the null and alternative hypotheses for this test. Also to identify the test statistics for this test. Also to identify the p-value for this test. So the terminologies here I have underlined, and we'll talk about as we go along. And then finally, he wants you to identify the conclusion for this test. So, methods. So there are two methods that we're going to do. It doesn't mean that these are the only two methods. These are the ones that we are going to do. So the first method is to compute the test statistic and the p-value. Now, one is a t-score, and one is an area under the normal curve, or the t-curve, t-distribution. The next method is simply to use the TI-84 calculator. You can also use a TI-83. I don't think there's any of the functions that we're going to use that's not on the TI-83. But if you have a choice, you should use the TI-84. So while you're doing the presentation, you should have your TI-83 or TI-84 with you, because we're going to be using it, and I would ask you to do computations or to search for something or a function on the calculator. All right. So let's take method 1 and break it down. Let's see. This can be done in 6 steps. So what's the first step? The first step is to formulate the null and alternative hypotheses. They are denoted respectively by H0 and H1. Sometimes we say H sub A. Instead of H sub 1, you say H sub A. Obviously, the A meaning alternative. So here we have the null hypothesis is mu is equal to 2.2, right? Remember I asked you to write down certain things? Well, the null hypothesis is mu is equal to mu 0. And I have it written down here myself. Mu 0 is 2.2. Hence, the null hypothesis is mu is equal to 2.2. Now moving on, we do H1 or H sub A is mu is greater than 2.2. How do I know greater than? Because if you look in the problem, it says, in parentheses, we're talking about showing that it's bigger than 2.2. Okay? The claim is because he found in the sample that the mean was 2.2, was bigger than 2.2. He believes that that's true in the whole population. So that's what the test is all about. So we already have the answer to one part of the question, part A, and that is the H sub 0 is mu is equal to 2.2, and H sub 1 or H sub A is mu is greater than 2.2. Now, let's zoom out of here and go to the next step, which is to determine the basic values and the test type. So the test type that we're referring to here is whether it's a two-tailed test, whether it's a one-tailed test. Well, not one tail. We don't say one tail. If it's a right-tailed test or if it's a left-tailed test. Okay. So the basic values are mu 0. I know you know that because it's on your little cheat sheet. X bar, which is the mean of the sample. The standard deviation S, alpha, which is this level of significance, which is usually given, and whether it's a two-tail, a right tail, or a left tail test. So let's write them down. Mu 0. Check these against what you wrote down before. Mu 0 is 2.2. X bar is 2.31592. S, you see I have that written there. And alpha is 0.05. The fact that they have given you all these places for the X bar and the S means that you have to work in this many places, because later on it's going to ask you to wrong maybe to 4 or 5 places. To wrong to 4 places, you have to work in 5 all of the time, not some of the time, all of the time. Otherwise, your answer will be off. Here, since we're checking to see, what was it? Mu greater than 2.2, then this would be a right tail. Right tail. This means that alpha is all in the right, is all to the right. So the comparison that we're going to be making would be to the area that is alpha in size, all to the right. I'm going to show that in a picture in a minute. But for right now, we just need to know whether it's on the right, on the left, or if it's in 2 pieces, one on the right and one on the left. So let's draw a picture. And here comes the picture. So we're going to put in, on the picture, we're going to show where mu 0 is, should be in the middle, right? No, I'm sorry, X bar should be in the middle, right? Then That's coming down like that. Draw a little line on the right side. Show our alpha. Right, that's my little shaded area there. That's the best I can do with shading. So remember I said alpha is going to be all on the right, right? So now let's put in the axis scale. So there's a t-axis and there's an x-axis. The x-axis is the data value. So the data value here is mu0 in the middle, and x bar is where we have calculated a new mean. So it could fall anywhere in this picture. It could fall to the left of mu0. It could fall to the right. In this case, it is to the right because we just compute the values. So look on your cheat sheet and you will see your x bar was, what was it? 2.31 blah, blah, blah. And mu0 was 2.2. So that tells me that x bar is to the right. Now we're going to find a t value corresponding to that x bar. So that basically is finding how far x bar is from mu0 and dividing by the standard error. And then we'll use that to find the area under the curve to the right, and when you go on the other side to the left of those symmetric points. So let's zoom out again, and now let's go to find a test statistic, which is equal to, like I just mentioned, you will take x bar minus mu0 because you are finding how far away this new x bar is from the established mean. And you're going to divide by, normally you would divide by standard deviation, but here we don't use standard deviation, we use the standard error, and the standard error is s divided by the square root of n. Just plugging in the numbers, you'll get this quantity at the top, and then the 4.30786, which was s, divided by the square root of n. N was 400. Then you get these two numbers, and then blam, you got your answer for the test statistic. So we can answer the second question, which is to calculate the test statistic, and that is 0.54 if we give that to 2 places of decimal. So next we need to calculate the p-value. The p-value, and we're going to use a function called t-CDF. We're not going to use normal CDF because we're using the t tables. It's a t distribution because sigma is unknown. That's why we're going to use that one. So you go from 0.53817 to 1e99, and remember that this function takes the degrees of freedom. The degrees of freedom is 1 less than n. So let's substitute that in there, and then finally we'll find the value, and the value is 0.29537. This value would be the answer to the question, what is the p-value? Now we're going to take this p-value, and that's what we're going to use to compare with alpha, and then draw our conclusion or come to our conclusion. So p-value is 0.295 and alpha is 0.05. So you could compare them, and you see that the p-value is bigger than alpha. If the p-value is bigger than alpha, what does that tell you? Well, we know in general, if the p-value is less than alpha, then we reject the null hypothesis. If the p-value is greater than alpha, then we fail to reject the null hypothesis. So clearly, in this instance, we will fail to reject the null hypothesis. So this is what we'll write down for our answer, fail to reject the null hypothesis. Notice We don't use any other language but that. So the second method is fairly simple. It's basically just using the calculator function. And this is where you find the calculator function. You hit stat on your calculator, then on the stat you'll see a couple columns, and one of them is tests. You arrow over to test, and then the function is t test. So just put in a little more details there. It's stat test t test, and then stats. Now I say stats because we were given the values. So sometimes you are not given the values. You actually have to compute the x bar and standard deviation. So you can put that into the calculator, into L1, and when you come to use this function, it will ask you, do you have data in this calculator? And you say, yes, I have the data. And then it will ask you where, and then you just tell it where the data is, and you can use it. But for our purposes, we just need to use stat. It's going to ask you for arguments. Most of the functions ask for arguments. The red that I have on the slide after enter arguments, those are what the calculator is asking you for. The black is what you have to enter. So for mu0, which is the established mean, you would enter 2.2. For the sample mean, you would enter the 2.31592. And for S, enter in that big long number. N, it's asking you for N also. It has to have N because it has to find the degrees of freedom. And it also needs it for computing the T, what is that? The T star, right? To get that square root of N. And then you also have to tell it whether you're testing for mu greater than mu0. And here the answer is yes, that's what I'm testing. Because there are others, you can also do mu less than mu0. Then finally, you'll hit calculate, and voila, you'll get your answers. The first number is T, which is a test statistic, or T star. P here is not to be mixed up with a proportion. As a matter of fact, in this one, there's no ambiguity. This is the P value. So if I ask you to do this problem and you chose to use the calculator, you would have to know that the P here represents the P value. So notice also that you must draw your own conclusion. The calculator will not draw the conclusion for you. So you would have to do a test. In other words, you have to compare P value to alpha. And remember that if P is low, if P is less than alpha, the null hypothesis must go. So you would reject the null hypothesis. Whereas if P is high, meaning P is bigger than alpha, then you will fail to reject, and that's the jargon that you use, fail to reject the null hypothesis. So, a couple notes. For left tail tests, the p-value is that TCDF, but remember now you're going from -infinity to the test statistic. So it would be -1 E99. That's our approximation for infinity. And we need the degrees of freedom. I was trying to remember the n-1. You need to include the n-1 because you need the degrees of freedom included. For two-tailed tests, you would find from the test statistic to 1 E99. Again, you're going to need the n-1. And this time you multiply by 2 because you need one piece on the right and one piece on the left. So that's the end of this presentation. If you have any questions, please give me a call. I would see you again next time. Talk to you soon.